Human beings have always realized that certain things are longer than other things. For example, this line segment looks longer than this line segment. But that's not so satisfying just to make that comparison. You want to be able to measure it. You want to be able to quantify how much longer the second one is than the first one. And how do we go about doing that? Well, we define a unit length. We define a unit length. So if we make this our unit length, so we say this is 1 unit, then we could say how many of those lengths are each of these lines. So this first line looks like it is, we can do one of those units and then we can do it again. So it looks like this is 2 units. While this third one looks like we can get, let's see, that's 1, 2, 3 of the units. So this is 3 of the units. And right here, I'm just saying units. Sometimes we've made conventions to define a centimeter, where the unit might look something like this, and it's going to look different depending on your screen. Or we might have an inch that looks something like this. Or we might have a foot that I won't be able to fit on this screen based on how big I've just drawn the inch, or a meter. So there's different units that you could use to measure in terms of. But now let's think about more dimensions. This is literally a one-dimensional case. This is 1D. Why is it one dimension? Well, I can only measure length. But now let's go to a 2D case. Let's go to 2 dimensions, where objects could have a length and a width, or a width and a height. So let's imagine 2 figures here that look like this. So let's say this is one of them. This is one of them. And notice it has a width and it has a height, or you could view it as a length or you could view it as a width and a length, depending on how you want to view it. So let's say this is one figure right over here, and let's say this is the other one. So this is the other one right over here. Try to draw them reasonably well. Now, once again, now we're in 2 dimensions, and we want to say, well, how much in 2 dimensions space is this taking up? Or how much area are each of these 2 taking up? Well, once again, we could just make a comparison. This second, if you view them as carpets or rectangles, the second rectangle is taking up more of my screen than this first one, but I want to be able to measure it. So how would we measure it? Well, once again, we would define a unit square. Instead of just a unit length, we now have 2 dimensions. We have to define a unit square. And so we might make our unit square. And the unit square we will define as being a square where its width and its height are both equal to the unit length. So this is, its width is 1 unit and its height is 1 unit. And so we will often call this 1 square unit. Oftentimes you'll say this is 1 unit, and you put this 2 up here. This literally means 1 unit squared. And instead of writing unit, this could have been a centimeter. So this would be 1 square centimeter. But now we can use this to measure these areas. And we say, well, how many, just as we said how many of this unit length could fit on these lines, we could say how many of these unit squares can fit in here. And so here we might take one of our unit squares and say, okay, it fills up that much space. Well, we need more to cover all of it. Well, there, we'll put another unit square there. We'll put another unit square right over there. We'll put another unit square right over there. Wow, 4 unit squares exactly cover this. So we would say that this has an area of 4 units, 4 square units, or 4 units squared. Now what about this one right over here? Well, here, let's see, I could fit 1, 2, 3, 4, 5, 6, 7, 8, and 9. So here I could fit 9 units squared. Let's keep going. We live in a 3-dimensional world. Why restrict ourselves to only 1 or 2? So let's go to the 3D case. And once again, when people say 3D, they're talking about 3 dimensions. They're talking about the different directions that you can measure things in. Here there's only length. Here there's length and width, or width and height. And here there'll be width and height and depth. So once again, if you have let's say an object, and now we're in 3 dimensions, we're in the world we live in, that looks like this, and then you have another object that looks like this, it looks like this, this second object takes up more space, more physical space than this first object does. It looks like it has a larger volume, but how do we actually measure that? And remember, volume is just how much space something takes up in 3 dimensions. Area is how much space something takes up in 2 dimensions. Length is how much space something takes up in 1 dimension. But when we think about space, we're normally thinking about 3 dimensions. So how much space would you take up in the world that we live in? So just like we did before, we can define, instead of a unit length or a unit area, we can define a unit volume or a unit cube. So let's do that. Let's define our unit cube. And here, it's a cube, so all of its length, width, and height are going to be the same value. So my best attempt at drawing a cube. And they're all going to be 1 unit. So it's going to be 1 unit high, 1 unit deep, and 1 unit wide. And so to measure volume, we can say, well, how many of these unit cubes can fit into these different shapes? Well, this one right over here, and you won't be able to actually see all of them. I could essentially break it down into, so let me see how well I can do this so that we can count them all. It's a little bit harder to see them all because there's some cubes that are behind us. But if you think of it as 2 layers, so one layer would look like this. One layer is going to look like this. So imagine 2 things like this stacked on top of each other. So this one's going to have 1, 2, 3, 4 cubes. Now this is going to have 2 of these stacked on top of each other. So here you have 8 unit cubes, or you could have 8 units cubed volume. What about here? Well, if we try to fit it all in, let me see how well I can draw this. It's going to look something like this. Obviously, this is kind of a rough drawing. And so if we were to try to take this apart, you'd essentially have you'd have a stack of 3 sections that will each look something like this. My best attempt at drawing it. 3 sections that would look something like what I'm about to draw. So it would look like this. So if you took 3 of these and stacked them on top of each other, you would get this right over here. And each of these have 1, 2, 3, 4, 5, 6, 7, 8, 9 cubes in it. 9 times 3. You're going to have 27 cubic units in this one right over here. So hopefully that helps us think a little bit about how we measure things, especially how we measure different things in different number of dimensions, especially in 3 dimensions when we call it volume. I have this figure here. You could call it a rectangular prism. And I want to measure its volume. And I'm defining my unit cube as being a 1 centimeter by 1 centimeter by 1 centimeter cube. It has 1 centimeter width, 1 centimeter depth, 1 centimeter height. And I will call this is equal to 1 cubic centimeter. So I want to measure this volume in terms of cubic centimeters. We've already seen that we can do that by saying, hey, how many of these cubic centimeters can fit into this figure without them overlapping in any way? So if we had this, in our hands, we could kind of try to go around it and try to count it, but it's hard to see here because there's some cubes that we can't see behind the ones that we are seeing. So I'm going to try different tactics at it. So first, let's just think about what we can observe. So we see that this one, if we measure its different dimensions, its width, it's 2 of the unit length wide. So it's 2 centimeters wide. It's 4 of our unit length. We're defining our unit length as a centimeter. It's 4 of our unit length high. So this dimension right over here is 4 centimeters. And it is 3 of our unit length deep. So this dimension right over here is 3 centimeters. So I want to explore if we can somehow use these numbers to figure out how many of these cubic centimeters would fit into this figure. And the first way I'm going to think about it is by looking at slices. So I'm going to take a slice. I'm going to take this slice right over here of our original figure. And let's think about how we can how using these numbers we can figure out how many unit cubes were in that slice. Well, this is 2 centimeters wide, and it is 4 centimeters high. It is 4 centimeters high. And you might be saying, hey, Sal, I could just count these things. I could get eight squares here. But what if there was a ton there? It would be a lot harder. And you might realize, well, I could just multiply the width times the height. That would give me the area of this surface right over here. And it's only 1 deep, so that also will give me the number of cubes. So let's do that. Let's find the area here. Well, that's going to be 2 centimeters times 4 centimeters. 2 centimeters times 4 centimeters. That gives us the area of this. And then if we want to find out the number of cubes, well, that's also going to be equivalent to the number of cubes. So we have 8 square centimeters is this area, and the number of cubes is 8. And if we want the number of cubes in the whole thing, we just have to multiply by the number of slices. And we see that we need 1, 2, 3 slices. This is 3 centimeters deep. So we're going to multiply that times 3. So we took the area of one surface, we took the area of this surface right over here, and then we multiplied it by the depth. That essentially gives us the number of cubes, because the area of this surface gives us the number of cubes in a slice that is 1 cube deep, and then we would have to have 3 slices like that. So we would have to have, this is 1 slice, we would have to have another slice, and then another slice in order to construct the original figure. So 2 centimeters times 4 centimeters times 3 centimeters would give us our volume. Let's see if that works out. 2 times 4 is 8 times 3 is 24. 24, let me do that in that pink color. 24 centimeters cubed, or I could say cubic centimeters. So that's one way to measure the volume. Now, there's multiple surfaces here. I happen to pick this surface, but I could have picked another one. I could have picked this surface right over here and done the exact same thing. So let's pick this surface and do the exact same thing. This surface is 3 centimeters. 3 centimeters by 4 centimeters by 4 centimeters. Let me do that in that blue color. Color changing is always difficult. By 4 centimeters. So its area is going to be 12 square centimeters is the area of this surface, and 12 is also the number of cubes that we have in that slice. And so how many slices do we need like this in order to construct the original figure? Well, we need, it's 2 centimeters deep. This is only 1 centimeter deep, so we need 2 of them. We need 2 of them to construct the original figure. So we can essentially find the area of that first surface, which was 3 times 4. 3 times 4, and then multiply that times the width, times how many of those slices you need, so times 2. And once again, this is going to be 3 times 4 is 12, times 2 is 24. I didn't write the units this first time, but that's going to give us the count of how many cubic centimeters we have, how many unit cubes we can fit. So once again, this is 24 cubic centimeters. And you can imagine you could do the same thing, not with this surface, not with this surface, but with the top surface. The top surface is 3 centimeters deep, 3 centimeters deep, and 2 centimeters wide, 2 centimeters wide. So you could view its area, or its area is going to be 3 centimeters times 2 centimeters. So that area is, let me do it in the same colors, 3 centimeters times 2 centimeters, 2 centimeters, which is 6 square centimeters. And that also tells you that there's going to be 6 cubes in this 1 cube deep slice. But how many of these slices do you need? Well, you have, this whole thing is 4 centimeters tall, and this thing is only 1 centimeter, so you're going to need 4 of them. So that's 2, 3, 3, trying to draw it as neatly as I can, 3, and 4. You're going to need 4 of these. So to figure out the whole volume, you're going to have to take that and multiply that times 4 centimeters, which once again, 3 times 2 is 6 square centimeters times 4 centimeters is 24 cubic centimeters. So it doesn't matter what order you multiply these in. You could view this, take the one area of one side, then multiply it times the depth, or you could take the surface area of another height and multiply it times the height or the width or the depth. And these are all the scenarios. But what it shows is it doesn't matter what order we multiply these 3 dimensions in. You could view it, you could take the 2 times the 4 first and then multiply by the 3, or you could take the 3 times the 4 first and then multiply by the 2, or you could take the 2 times the 3 first and then multiply by the 4. When you're multiplying, it doesn't matter what order you're doing these in. And so if you have a rectangular prism like this, and you know it's 3 dimensions, you know it's 2 centimeters wide, 3 centimeters deep, and 4 centimeters tall, you can say, hey, the volume of this thing, the number of unit cubes, the number of cubic centimeters it can fit is going to be 2 centimeters times 4 centimeters times 4 centimeters times 3 centimeters, which we've seen 3 times already is 24 cubic centimeters. A water tank is 12 feet high, 5 feet long, and 9 feet wide. A solid metal box, which is 7 feet high, 4 feet long, and 8 feet wide, is sitting at the bottom of the tank. The tank is filled with water. What is the volume of the water in the tank? So let's think about this. We have a water tank. It's 12 feet high. Try to draw this as good as I can. So it's 12 feet high. It's 5 feet long. So this looks like that's about 5 feet. And it's 9 feet wide. So this is my best rendition of what the tank looks like. So the tank might look something like this. That is my water tank. Let me draw it. Draw the whole thing. So there's my water tank. And I'm going to make it transparent so that we can see what's going on inside of the tank. So here we go. There's like a helicopter outside or something. I don't know if y'all hear that. But let's see. So there is my water tank. 12 feet high, 5 feet long, and 9 feet wide. 9 foot wide. And then they say there's a solid metal box, which is 7 feet high, 4 feet long, and 8 feet wide, sitting at the bottom. Sitting at the bottom. So let's see if I can draw that. So let's say it's 4 feet wide, 4 feet, or I guess we could say 4 feet long, 7 feet high. So let's see, 4 feet might look something like this. It's 7 feet high, which might look something like that. 7 feet high. Obviously, I'm not drawing it perfectly to scale. 7 feet high and 8 feet wide. So it might look something like this as it's sitting in this tank. So this is that metal box. And and they say it's a solid metal box. It's not like any water can fit in here. So let me make it as a solid metal box. So this is a solid metal box. And then I'm going to fill the whole thing. I'm going to fill the whole thing with water. I'm going to pour water into this thing. And the water is going to start filling up. And it's going to fill up all the volume of the tank except where the metal box is. It's not going to be able to fill in that volume because the metal box is solid. So it's going to fill up. We're going to slowly fill this thing up around the metal box. So what's the volume that it's going to fill up? Well, it's going to fill up the volume of the tank minus the volume of the metal box. It couldn't fill in the metal box volume. So let's figure out what that is. The volume of the tank is going to be 9 foot by 5 foot times 12 feet. That's the volume of the tank. Tank volume. And from that, we want to subtract the metal box volume. So minus 4 foot by 8 feet by 8 feet, 8 feet by 7 feet, by 7 feet, by 7 feet. This is 4 feet wide. It is 8 feet. What do they say? It's 7 feet high. 7 feet high. It's 4 feet long, and it's 8 feet wide. 8 feet wide. So this right over here is the volume. This is the, I guess we could call it the metal box volume. The box volume. And so what's in between, or when you take the tank volume, subtract out the box volume, that's how much the water can actually fill in. So I only do the water partially filled, but once it's already filled in, the water is going to go all the way to the top here, and it will fill in everything except for where that blue box is. So let's figure out what this value is. So 5 times 12 is 60. 60 times 9 is 540. And then in blue here, let's see, 4 times 8 is 32. 32 times 7 is 210 plus 14, which is 224. So it's minus 224. Minus 224. Did I do that right? I don't want to make a careless mistake. So 32 times 7. 2 times 7 is 14. 3, which is really a 30 here. 30 times 7 is 210, plus another 10 is 220, so 224. So this is going to be equal to, let's see, 500 minus 200 is 300. 300, and then 40 minus 24 is 16. 316, and our units are in cubic feet. So the volume of the water in the tank, 316 cubic feet.